Okay. I prepared slides, but in the end I figured Blackboard is better. Okay, rough path. Let's start perhaps with path, and let me be very bold and just tell you a list of topics of maths, of applied maths, where paths occur, and I'm not going to write them down. I will just read them out, and you may add to this list as you please. So clearly, when you look at differential equations that model some evolution in time, then you can think of this as a path, and depending if you look at ODEs or PDEs, the state space may be finite or infinite dimensional. In geometry, we need paths all the time. For instance, when you look at geodesics between points. In algebraic topology, when you study homotopy theory, you need paths. Stochastic processes deal, by and large, with random paths. In statistics, you have time series data. You can think of them as paths. In finance, the price evolutions are paths. Control and signal theory are built on paths. And in music, the audio streams are paths. So they're everywhere, not only in mathematics. Okay, so for now, I will not do rough but smooth paths. Smooth path. And by smooth here, I mean smooth enough that you can compute certain iterated integrals. So for me, C infinity or just rectifiable makes no difference. I want to write down these iterated integrals. I want them to be Riemann-Stieltjes type integrals, and you could move it, the meaning of smooth, up to p variation for p less than 2 if you must, but let's not worry about it. And so what I have in mind here is a path, and let me draw a picture here. Here is a path. Let's see if that matches my slide here. Yeah, it's pretty good. So, and many things I will say are invariant under parametrization, so it doesn't really matter that you take 0, 1 here. You could take 0, t or a, b. It doesn't matter. And I want to attach an object to this path, which is called the signature. So S. So let's make a pretty picture again. And it should be the same path. And what it is, by definition, it's some sort of a formal series. And the first term here, let me move on here. The first term in this formal series is just scalar 1. That's not very interesting. The next term here is the integral from 0 to 1 dx. That's also not very interesting. I'm challenged by the hate of the blackboard here. Okay, so I mean, we're looking at the smooth paths, so there's no question that the meaning of this guy here is just this vector here. Right? It measures the net increment where you end up minus where you start. So the next one is the iterated integral, 0, 1. Let me see if I start my convention here. Yes, I do. So I want to switch to a better notation here. And so we integrate over the simplex. Here, 1, something like this. dxs dxt. Okay. And you can guess how this continues. Dot, 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 dot. And so let's do a little bookkeeping in which space we are. Well, this is scalar 1. Here I look at some d-dimensional vector. This is a d times d matrix, and the dots here, I mean, you build up 3, 4, 5 tensors, etc., etc. So this takes values in, well, so we just tensorize Rd, and then k runs from 0 to infinity. Now the convention is for the 0th tensor power are just the scalars, right? So this is a convention here. This is just R. And then, well, strictly speaking, if you do linear algebra and this direct sum, only finitely many are allowed to be non-zero. So you should sort of close it up, and then you call it the tensor algebra. Right? It's like the difference between polynomials and formal power series. Right? So you just need enough space to put in all this information, okay? This way you have a map that takes a path, a sufficiently regular path, and gets you a point in this infinite dimensional space. So far, so easy. Well, the two things I want to mention here in this construction here. There are two things that are lost, that are obviously lost, and you may or may not care about them. One is the starting point. Right? At no point did you store this information because you just look at increments, okay? So that's one thing. The other thing you lost is the parametrization, because these guys here are iterated Riemann-Stieltjes integrals. They just look at the increments. If you decide to reparameterize your path, that you run a little bit faster here, a little slower here, it wouldn't change a thing, okay? So everything here is defined modulo starting point and parameterization, okay? So we do not keep track of starting point and the parameterization. Right. The other thing, I mean, the notation here is not quite perfect. I mean, these dx's, they're increments in Rd, and alt should come in at 2 tensor here, so I really should put in this here, okay? So won't fuss much about it, but if you take two vectors, v tensor w, then in coordinates, I just mean vi wj in coordinates. Okay, that's all you need to know about how to tensor product vectors. Okay, so far so good. Now, what operations can you do with path? Well, you can take one path. So here's our x path. And then you can take a second one, and let's call it x tilde blue. So, right. Another path. So let's make it blue. And, well, let's see how it should look like. Let's make it a little hump like this. Okay. So you can do the same game here and compute the signature of this blue little piece. And then what's the most natural operation on such path segments? Well, you can concatenate them, which is what we've done here already, right? I mean, if you wish, you can consider this as one path parameterized by 0, 2, in which case you better reparameterize this one that it runs from 1 to 2 so that it all fits together. So let's ask ourselves, what is the signature of this thing here? Right? So we are, right. So we have this one, and then we have the signature of this little chunk here. Blue it is. Right? And what we would like is some operation here so that the whole thing becomes the signature of the concatenated path, okay? So it's one question. You can ask a similar question, what happens, I mean, I didn't write it, but they are invariant under reparameterization, but it does make a difference if you reverse time. Then the net increment switches the sign. So I can make this here. So here's another question. If you define the backward version of your path, oops, yes, like this, as just being, you run it the other way around, okay? The picture is not perfect, but it's good enough. So, well, if we must, we can give this one a name here. So this oops. I'll be done with colors in a few minutes, so not to worry. So you can make this formula an operation between paths. And if I give you two paths, star means you concatenate them. Okay? Okay. So the question is, what do these have to do with each other? And the answer is surprisingly pleasant. So here's the answer. Or let's say towards the answer. I'm sort of going along, and then the answer will pop out. So the first thing is we may regard X concatenation with X tilde as one path defined on 0, 2. Well, we already mentioned this here. If I change this to 1, 2, then that's it. There's nothing else to do. So that means we can compute the signature very easily. Right, by definition, it's the same expansion here, but instead of 0, 1, it's 0, 2. So it's the same thing from 0 to 2 dx, and then less than 2, and so on. Yeah? So now, let's look at the nth term here. Okay, and I need a better notation here. So let's agree that, I mean, here basically you have the 2 simplex. Let's call this here something like, how should we call it? Delta 2 over 0, 2. Right? 2 simplex, and if you do it n times, then you naturally go over the n simplex. Right? So this is the, well, you know what it is. And so on. Right? And now you can play a very silly game that you say, well, we all know that integrals are additive if you integrate over disjoint domains. So let's just decompose this n simplex here. So maybe I should write it out again. So this is the set of all n tuples that are ordered here up to 2, right? So these guys run here, right? And now I can say, well, if you give me any such n tuple, then, you know, no matter which one you look at, there will be a certain number to the left of 1, and a certain number will be to the right of 1. Right? And you can do this in a disjoint fashion by just counting how many are on the left side and how many remain on the other side. So in other words, we can write this as a disjoint, or essentially disjoint union. I don't care about null sets. In the end, we integrate. Everything is smooth and no point masses or so. So I want to write it as a a union as follows, and perhaps to avoid silly things, let me split up the extreme cases. So it could happen that all of them are, it could happen that all of them sit here. Right? And then it could happen that all of them are here. Well, and in between, well, again, you look at some union here, and what you should observe is that basically we look at the product of lower dimensional simplices, right? So you have n minus k here, n minus k, 0, 1, and then Cartesian product, 1, 2, okay? And k here runs between 1 and then n minus 1. Okay? So you could do this from 0 to n, but then you have to define what we mean by some 0 simpler. So this is completely explicit. Okay? So now this allows you to split this up. Right? And what you see is it splits up in one piece corresponding to this domain. And this is precisely the level n signature of the path x. Then it splits up in the level n signature of x tilde, which corresponds to this domain here. And there's some chunk in the middle here. And if you digest all this, then you can write it in a very slick form. Namely, you can say that this guy here, right, equals summation over k 0 to n here. So now we put the extreme cases with us. And all we're doing is we're looking at one dx okay, with the convention that the integral here over the 0 simplex should just be scalar 1. Yeah. And so that's already it. Now you just need a slick notation for all this. Namely, if you introduce the projection operator, right, so there's a natural projection from T RD. So this was our tensor algebra. And if you just look at the level of n tensors, then you can realize this through the obvious projection operator. And in terms of this operator, this relation now becomes very simple, because what we've really done here is we look at the signature of the concatenation x tilde, and what we find is that it splits up in the product of these by k and by n minus k projections of the respective signature of x and x tilde. So by k of x right? So here you pick out a k tensor, here you pick out an n minus k tensor, you tensorize it, you get back to an n tensor, and k to 0 and n. Okay? So now it's just a matter of furnishing this space here with a suitable algebraic operation, which is the tensor product, so that this one becomes even slicker. So I'll do that in a second here. Namely, need more space here. Well, let's see what we can do here. This may be rough. All right. Okay, let's keep this for now. Okay. So remember, all these guys here take values in T double parenthesis RD, this full tensor algebra. And so I'm claiming what we have over there is nothing that S X tensor S X tilde here, provided I define this guy here appropriately. Now, we have already used it, but we have used it so far only in the way that we take a K tensor and then we take an M tensor, and the tensor product, just by putting them next to each other, becomes an K plus M tensor, right? But now here, we're looking at the tensor product defined on the whole tensor algebra. So now we are allowed to take one plus a vector and tensorize it with a matrix, and everything is possible here. So we just have to define this properly. And the definition here is very simple. So you say A tensor B equals Z with A equals A0, A1, and similar for B and C, precisely if you have B, Z similar, precisely if you have that the nth component of C here is given by collecting the guys in here, A, K, and then tensor B n minus K, K equals 0 up to n, okay? So there's no surprise if you're used to the calculus of non-commutative power series in D indeterminates, it's the same thing. So, okay, so this one is okay, right? And so that's a very clean answer to the question that we came up with, namely, we fully understand how concatenation translates to this level of signatures. This runs under name Chen's relation. So let's see how much time we have. Plenty. Okay, that's good. Now, this space here becomes a non-commutative algebra. What's the unit element? It's just scalar 1, 0, 0, 0, 0. So, this becomes a non-commutative algebra. And again, let me just point out the unit element 1, and you check immediately that with respect to this product here, that is the unit element. Now, a little bit like in the calculus of formal power series, if you have a power series that starts with a non-zero scalar, then there's a formal, you can look at the inverse. Right? So the same is true here. And what we can do is, so says conveniently, we always put a 1 here. So this convention was used over there when you deal with these borderline cases, k equals 0 and k equals n. But so in particular, we can always look at the inverse here. right? I mean, not every element in here is invertible. If you just take 0, 0, 0, it's not. But those that start with 1 are. And how do you get them? Well, just remember the Bauer series for 1 plus x to the minus 1, and that's it. You have a Bauer series calculus here because you have the product structure, right? So this you can define. On the other hand, remember earlier I said you look at the path on a fixed time interval 0, 1. You can run it backwards, and it's a fun exercise to check that this is right, this complement sort of chance relation. Exercise. Okay. Now, what else can we do? Well, you can do everything that you do in power series analysis. So the exponential map is well defined. The logarithm is well defined, provided you start with something that's, that's non-zero, similar to here. So let's play a little bit around here. So let me define the exponential map here. Okay, very easy. Given any element A in this tensor algebra, exp A is, no surprise, scalar 1 plus A plus A tensor square divided by 2 factorial, and you know what's coming. And let me just point out one thing. Usually, we will use this exponential for elements A that have 0 scalar component. Right? And if that happens, then there's no convergence issue here. Because if the lowest element in this series is a 1 tensor, then here you already have a matrix, and then at 3, etc., etc. So at every given tensor level, there are only finitely many. There's no convergence issue. Of course, if you take A as a scalar itself, then this is the usual series, and you have to think about convergence. But of course, we did it all 20 or 50 years ago. So, okay. Exponential map. So here's an exercise that is very pleasant, very easy. So you take the simplest path that you can imagine. You take a straight line. Okay. So, and let me abuse notation a little bit here. I just look at some vector v, and then I turn it into a constant speed path by saying xt is by definition v times t. Yeah, can you see this? Okay. So if v is a vector in Rd, then you've created a quite trivial path in Rd. And in particular, you can start asking yourself silly questions like, what is the signature of this simple path? And if you think about it for 20 seconds, you realize the signature of this path is precisely the exponential of v. Just plug it in. So the signature here of this path x here is just e to the v. Not the usual exponential, of course, it's a tensor exponential. You give me it? Okay. So that was easy. So we can do more because we have chance relation. So let's move maybe here. So let's continue this little example here. And now our path here, and let me do a little abusive notation here. It's so more awkward to have this vector and then this path, because once you have the vector, you have the path, right? So let me just identify this whole path here. Let me just identify this with this v. And so now you take 3 paths, or 3 vectors, v1, v2, v3. And what's the signature? So here's the picture. V1, V2, V3. So every vector corresponds to a little path, and you can concatenate them, and then you get a path. You get a path which you may call V1 concatenation with V2 concatenation with V3 here. Right? So this path here is what you get by following these three vectors here. And what is the signature of this? Well, we have chance relation. Chance relation allows us to put things apart. Right? So we split it up, and then, of course, we know that the answer is e to the v1 tensor e to the v2 tensor e to the v3. Okay, that was easy. Now, you may remember that even in the context of matrices or any non-commutative algebra, order matters. It's a non-commutative setting. But there's the Campbell-Hausdorff formula that tells you what's going on. So if you use it, then you get plus v3. And then there are additional terms, namely the commutators pop up. So plus, with a 1/2 v1 v2 plus, and I spare myself the pain of going further. But the point is that there is some non-zero stuff here, and this is the Campbell-Hausdorff-Baker formula, which you can give elementary proofs in this context, or not too. You have to prove something, it's not true. Yeah? But the point I want to make is that what you get here up in the exponent is not just anything. It has a specific form. Namely, you take vectors. So this certainly lives in the span of the basis vectors in RD. So I mean, this is a vector in RD. But then you get stuff that are obtained by taking Lie brackets. So this is what people call a Lie series. Lie series. And it won't stop, but it's formal, so there's no problem. So what we learned is that if you look at piecewise linear path and you compute the signature, then you get exponentials of Lie elements. Right? It's a log Lie series if you want. Okay? So, and since piecewise linear approximations are pretty good for smooth path, this passes to the limit, and you can use this to show theorem. Okay. Signatures of smooth path. Let's see how I called it. Log Lie series. Well, if you take the log, then you're left with the Lie series. R log Lie series. Okay, and you also hear the name group-like. Okay, well, so little by little we get into non-trivial territory. And now let me spin this example a little bit further, or actually let me modify it a little bit. So, is it okay if yeah? I mean, as a matter of fact, I have full slides if you're interested. So let's modify this a little bit. Let's take another vector here, but now let's backtrack. Okay, and to make this plain, so I take my V3, I take it minus V2, which means I backtrack here. And then the same game here, I take this guy here to me, so I backtrack here. So in the end, I am where I started. So what happens to the signature here? Let's call such a path a tree-like path. Okay, I mean, it doesn't look much like a tree, but if you add, another 2n vectors, and you can make it look like this, and tree-like. Okay. So what happens to the signature of such a tree-like path? Well, if you look here and here, and you combine them, you see it shrinks together to nothing. So just as a consequence of chance relation plus this, signature of path run backwards, you see the tree-like path have a trivial signature. Okay. So let me remind you, in the very beginning, I pointed out that when you compute the signature, you immediately lose 2 bits of information: starting point, parameterization of your curve. Here we see that any tree-like excursion, if you have a path and you sort of attach a little tree to it, you will never tell in the signature, because it will, on the level of signature, it shrinks to nothing. So it's a remarkable theorem. In the smooth case, due to Chen; in the rectifiable case, due to Lyons and Ben Hamley, that this is all the information you lost. And this was a, let's see, I think a 100-page paper in the Annals of Maths 4 years ago, so I'm nowhere near giving a proof here. It's a theorem. Let me say Chen, which year? So Chen, I think it's 57. Fabrice, you know? Anyway, around plus minus a decade. Anyway, and this was 10, okay? And what they show is that signatures, or the signature, determines the path. The path modulo these 3 things. So you can't recover the starting point. You can't recover the parameterization. And you can't recover this tree-like stuff. Okay. So there's a lot of structure in these signatures. Now, there was no probability so far, and there was nothing rough so far. So we should do something about this. So I will try to look at the time as well. I have a full hour left. Is it correct? Yes, no? Yes? Okay, good. So now, probability. Something with probability. And just out of curiosity, how many people here are reasonably well trained in probability theory? Okay. Okay, let me say it differently. Okay. Who knows what a Poisson process is? Okay. Okay. I mean, if you want, you can check your emails for 15 minutes, and then we're going back to deterministic stuff. But so let me look at some IID family of d-dimensional random variables. Okay. And now I define the so-called compound Poisson process. So what it means is that at you look at the standard Poisson continuous time counting process. So there are these famous clocks that ring, and the times between these clocks ringing are independent exponentially distributed random variables. That's how you can build a standard Poisson process. So if this is your standard Poisson process, then you can decide whenever the clock rings, in the usual counting process, whenever it rings, you get €1 or one customer comes or something, right? But you can also agree that whenever the clock rings, you jump. And you jump from a new realization of this random variable. So they should be independent, right? So the way to write it down is to say, well, you look at nt. Nt is how many jumps sort of have happened up to time t. And if no jump happened, then it's 0 by convention. And then every time you jump, you grab one of these random variables, and they're random. Okay. So in the event of n jumps, so nt equals n, so that means n jumps. Well, you know what this xt is? Well, do we? I mean, if you draw a picture here, you may think you start at the origin, okay? And then the clock rings and you jump here. So this is your J1. And the clock rings and you jump here. There's no path here. I mean, there's a piecewise constant path if you want. And it's up to you what you do in between. I mean, you can keep it here, then jump here, but this doesn't fit really the picture of continuous path that I had. So let's do something very simple. Let's just say we connect them with straight lines. And since the signature, which we are after here, doesn't care about parameterization, I mean, you can think that you stay here a very long time and then run here very quickly. So it's not crazy. So if I use my abusive notation from earlier, I could say that in this event here, the resulting path is the concatenation of these n jump bits, right? So my notation from earlier, this is J1 concatenation with Jn. So that means we know what the signature is. So that means the signature S equals e to the J1 tensor Jn. And now probability comes in, namely, I can do an elementary computation now where I say that the expected signature, so expected value of S, so let's make, so just condition on all these events, and I know what the probabilities are because, after all, n is a Poisson process. And then I sum up the contribution that I get from every event, which is of this form here. And so what you have is really the sum of, now you remember that these are all IID, right? And independent. So the contribution of one is e to the j, right? And because they're independent, I'm allowed to split it up. Tensor n. And then I get the weight, so here. So this is either one, doesn't matter, they are IID, right? And then I get the weights, the probability that nt is n. Is n. And so now it's a short computation that, I mean, it forces you to think a little bit in terms of tensor algebra valued quantities, because after all, this here lives in the tensor algebra, so then you take the expected value, right? So note that the expected value will make you leave these group-like elements. There's no, I mean, it's not a linear space. So that's fine. So in the end, you will get something which lives in the tensor algebra, but not in this log Lie series. And the answer is very simple, namely, it's exp And for what it's worth, let's fix the time. It's okay. So there's a t times t. Where's t? T is here. I mean, you run everything up to t, right? This is right. T is a fixed parameter if you want. And then you have a Levi-Khinchine type result. So e to the y minus 1. Right? And then you have a k dy where, oh, here it's even easier. There's a mu dy, where mu is the law of j times the intensity of the Poisson process. Right? So let's take this at unit rate. And so the law of these j's is mu, and then you don't have to scale the measure. Okay? So if you know the Levi-Khinchine formula, or the moment-generating function of pure jump Levi processes, then this looks familiar. But beware, this is not the usual formula, because what you have to do here, integration is over RD. So I don't have space downstairs, so it comes upstairs. Integration here is over RD. But then you take y, which is a vector or one tensor, you stuff it in this tensor exponential, you already get big stuff here, and then the whole thing comes again in the tensor exponential, and out comes whatever it becomes. It's a big mess, but if you go for this representation here, it's very clean. So this is just the beginning of a big story that I'm not going to continue here, because there's a full-blown theory of Levi rough path, or rough paths with jumps actually, and Levi rough paths, and you can develop this in great generality. So I shall say no more here. But let me move to another process that we like very much, which is Brownian motion. Brownian motion. Right? So let's play the same game and ask, what is the expected signature of Brownian motion? And for those of you, so I suspect everybody knows, at least on some heuristic level, what a Brownian motion is. So we have some random walk, scaling limit, okay. What was really behind this t here? I mean, we studied everything to time t here. The reason this t shows up here, I mean, it came out from the computation, but really had to do with the fact that the underlying process here has independent increments. And the same was true for the lift, provided you think in the group. Now, Brownian motion also has independent increments, so it's very, so expected, so signature of Brownian motion. So I'm cheating you a little bit, because signature of Brownian motion, what is it? Well, the iterated integrals of Brownian motion, but which ones? I do not want to take the E2 ones, because then they all have zero mean, and you know, it's not interesting. So for those who know, I want the Stojanovich one. But if you don't know about this stuff, you can just think of Brownian motion. You modify the sample pass a little bit, epsilon, now everything is smooth. And then you pass to a limit. In fact, you can pass a limit either the inside or outside, it doesn't matter. That's what it is, okay? So if you don't know what it is, think you modify and pass to a limit. And then you certainly expect something similar to happen. And I should, again, fix my time horizon. So on 0t. Then from the independent increments of Brownian motion, I also expect something like this. Now, but what's inside? There's a little trick. I mean, you can go ahead and compute, and in Fabre's book, there's a nice computation. You write down a differential equation, so on and so on. But there's a simple observation here. Due to Atul Shekhar, who observed that there's only one possible entry here that's consistent with Brownian scaling. Because if you go to these higher levels, you know, Brownian scaling has the square root t scaling, and if you go to the higher levels, to the nth level, say, you have a, you know, t to the power n over 2 scaling, and there's only one n that's consistent with being linear in t. This is n equals 2. So only for n equals 2 is it true that n half equals 1, which is the one here. Right? So the only one that's consistent with Brownian scaling here is a 2 tensor. And then it's very cheap, because writing down the first iterate integrals to compute an expected value, that's an exercise for probability 1.1. So must be a two tensor. And of course, this is a result specific to Brown motion. Brown scaling. And then you can identify it, and in fact, you see it's an easy direct computation. 1/2 it. This is the d-dimensional identity matrix viewed as T tensor. Okay, so you can extend this game a little bit. So nobody forces you to work with standard Brownian motion. If you take a Brown motion that has covariance A, so if you change this to, so take with covariance A, so I'm a physicist here, 2 bars means a 2 tensor, symmetric, right? Then the formula becomes, okay? So again, what you sort of would expect from a Levy-Khinchin type formula. So now the reason I'm mentioning this is because there's a little paper here, this joint work with Terry Lyons and Paul Garcia, who's here. So just this little footnote here. It's a recent paper by Terry Lyons, Paul Garcia first, Terry Lyons and myself, where we consider a physical Brownian motion. That means the velocity is modeled by some Ornstein-Uhlenbeck process, and you pass to the zero mass limit. So that's a well-known result and very easy to prove, in fact, that you converge to a mathematical Brownian motion. So more or less physical Brownian motion, the zero mass limit is a mathematical Brownian motion. If you look at the expected signature, that ceases to be true once you're in a magnetic field. Okay? So it's still true that you converge to a mathematical Brownian motion, but once you have a charge on your particle and a magnetic field, which manifests itself as in the Ornstein-Uhlenbeck dynamics, you have some antisymmetric part in this drift term, then you actually converge to Brownian motion, but on the higher iterate integral, something else happens. So you can tell a story about Levy area, how that changes, but here at this level, it's quite striking. So if you take, again, this Brownian motion here, Brownian motion, so assume to have a unit charge, otherwise it wouldn't care about the magnetic field. In magnetic field, then you have the following result here, that this is still true, but this here changes to some A tilde, and A tilde is a 2 tensor, but not symmetric, okay? Not symmetric. So, although at many places it looks like, Levy-Khinchin and standard stuff, you dig a little bit and it's not so standard. Now, who cares about this expected signature? I didn't give much motivation. I just said, let's compute and let's see, and it happens, and it's closed form. It's nice. This expected signature tells you an awful lot about the process. It contains, for instance, under reasonable growth assumptions, it determines the law of the signature, so which is this random entry in this tensor algebra. And if you think of stochastic Taylor expansions, this is all you care when you do simulations or something. So a lot of information is there. And I should say that on Wednesday, there will be a young gentleman from Oxford here, Ilya Cheverev, and he will speak about his work on how to quantify this. So I recommend. Now, there's a meeting to Subriemannian geometry, amongst other things. So I should point out a little connection here. And now all these spaces here are infinite dimensional. And we don't want to do infinite dimensional Subriemannian geometry here. But there's an easy way to make it finite dimensional, you just truncate. So let's do this. The organizer actually asked me to consider a short break, so now? So let's make it short though, 3 minutes or so.
May I ask you a rapid question? In the definition of the exponential of element in TDRD, so 1 plus I
yes,
plus,
yes.
So we are assuming a structure of convergence, also a convergent power series to make sense to an infinite sum of elements in.
Right. So if it, I mean, as I said, if you look at, if you look at some element, let's say A, right, which happens to start at scalar 0, then A1, A2, which effectively is, I'm not sure it's a case in all computations. I mean, remember, the signature of straight path was E to the V.
Yes.
So in this case, there was a V here, there was 0 elsewhere. Right? In the expected signature computations, we actually had just a 2 tensor, so there's something here, 1/2 I. So this is always the case. Right?
So I can do the exponential of an element which starts with 0, essentially.
Right, so whenever you look at the exponential of something of this form here, there's no convergence issue, because if you look at level n, then you know they're only finitely many, so you're good. Now, if you had something here, it's not a catastrophe, right? But then you have to look a little bit about convergence here. Right? But it, I mean,
so if you have 0, the nth element is a finite sum of.
Right. And to make my point even clearer, in this whole business, I mean, we all love the exponential function, but here I've never encountered one where you had a good reason to put a non-zero value here. Right? I mean, what's a little bit behind it is you should think of there's a Lie group sitting in this tensor algebra, which is the one, which is those elements that start at scalar 1.
Okay.
Right? Because if you take 1 plus something, right, and you multiply it, you preserve it. If you do minus 1, you also preserve it. So, and he has the benefit that every element in this space is really invertible, as opposed to this space. Right?
Okay.
So then it's a Lie group.
Okay.
I mean, don't worry about the infinite dimensional aspect. You can truncate the level n as fine dimensional. And it's a super simple Lie group because it's essentially an alpha in space.
Okay.
What is the Lie algebra? Well, since you never move the scalar 1, the tangent space is just the one where you don't move this one. So those with the 0 entry here are the Lie algebra, right?
And so again, okay.
So you actually have a very simple example of an exponential Lie group. This is why you map from Lie algebra to Lie group, which is the good reason why you always have 0 here.
Okay. So it's bijecting in this case.
Absolutely.
It's
Perfect, yeah.
It's
I mean, as far as Lie groups go, this is the best of all worlds, right?
So we have an logarithm that...
Yeah.
Okay. Okay, thank you.
Welcome. Okay, I think we can resume here. So I have one slide, and it will become a little bit on the blackboard here on Subriemannian geometry. So what's the relation here? Again, I don't want to do infinite dimensional Subriemannian geometry. There's no need. So what we can do is very simple. We truncate this expansion here. So now we're in a good finite dimensional setting. N is arbitrary. And now, let me define the set of all points in here that you can reach by signatures of smooth path. Okay, and I mean it seems like the natural state space here because you just write it down and this is where it all lives. But this is a way too big space, sort of wasteful. I mean there are all sort of nonlinear relations here that I ignore, that I don't see here. So let's try the following here. So Sn is the signature that you compute and truncate at the nth tensor level, or beyond the nth tensor level. And then Gn here is defined as, again, everything that you can get by looking at signatures of smooth paths. So X is smooth. And once more, it wouldn't make a difference. I mean, here there's a little lemma to prove if you wish, but it wouldn't make a difference if you replace smooth by C1 or rectifiable or even Q variation for Q less than 2 and then define these iterate integrals in Young sense. It wouldn't make a difference. I mean, you have to show that it is the same, but it doesn't make a difference. Okay, so if nothing else, what you get here is a subspace. And if you wish, we always put the 1 here, right? And so we can hardwire this, if you want, we can. So now this equality is not true anymore, but if I want to insist that my scalar coordinate is 1, I can indicate it by putting a little 1 here, right? The advantages of this space has a group structure. Yeah? There are inverses, you can multiply, so it's quite trivially a Lie group. And the Lie algebra, the tangent space, is simply given by the same space, but you're not allowed to wiggle in the 0 components, so it's the same thing with a 0 here. Okay, so a super simple example of a Lie group, which is a manifold, of course, it's just the usual Euclidean space. Okay, now what do we know about this Gn that I defined here? Well, we had a theorem that told us that signatures are always log Lie series. Okay? Well, the same is true if you just truncate, but instead of a series, you may want to say polynomial or something. Yeah. So you clearly have that Gn is a subset of exp, and here, if you want, are all the Lie polynomials up to level n. So let's give them a name, frac Gn Rd or something, right? And these are the Lie polynomials. Okay. Now, actually you have equality here. Okay, and since this is a workshop on Subriemannian geometry, I suspect the majority of the audience is well aware of or knows by heart Chou's theorem, right? Getting from A to B in a Subriemannian manifold. And so you can view this as an implication of Chou's theorem. I will just quickly indicate how you look at this problem, and then we're going away again from Subriemannian geometry. So all you have to realize is that the signature here, all right? I mean, we defined it in a static way of saying we look at 0, 1, and we write down the iterated integrals. But there's a dynamic point of view where you say, well, let's look how the evolution happens when I do it not on 0, 1, but on 0, t. So let me say it this way. Sn of x is actually the endpoint, say S1 given by, and now I have to tell you the evolution for S, right? So S T dot equals so this is the okay, let's make it with dots for Jin. Okay, I could have written ds equals s tensor dx, but everything is smooth, so x dot. Okay, and you start at the unit element. Okay. So this is a differential equation in the truncated tensor algebra. It's an ODE and Tn. Right? And, well, you may want to write it in a more familiar control theory fashion. So I would like to write it as some driving vector fields. Let's call them ui of S, and then need some space here, and then perhaps some x dot I t, then summation over I equals 1 to d. After all, x is d-dimensional, and now it starts to look a little bit like a control problem, right? So you have driving vector fields u1 up to ud, and we should write down what they are. It's not difficult. So ui s equals S tensor EI. So EI is the standard basis in RD. The basis vectors are viewed as 1 tensors, and this is the rule. This is how my vector fields are given. Okay? And then it's a pleasant little exercise to check that the tangent space Gn RD. You want to look at the tangent space at some element G. Right? And then this is precisely the Lie algebra generated by these vector fields U1 up to UD. right? So in other words, you have this bracket generating Hamanda type condition. And now it's clear from Joe's theorem that you can always get there, and in particular, you get the desired equality. Okay? So if you want, there's self-contained proofs of all this in my book with Victoire. So you don't have to read Montgomery or open up all this Subriemannian stuff. You can, of course, but the situation here, as I hope you see, is much simpler. Right? You're not talking about some abstract Subriemannian manifold. In fact, you talk about a very concrete exponential Lie group. You have a global chart. I mean, life is good here. Right? You should appreciate. With a Subriemannian structure, of course. Okay. So this would be another good moment for a break, but we probably shouldn't. The reason for rough path theory is really, or the origin is stochastic integration. And as you may know, Brownian motion has very poor sample path regularity. And in particular, you cannot define, any sort of Riemann-Stieltjes type integration against Brownian motion. It doesn't work. Well, that's why we developed stochastic integration, and it's a probabilistic construction, and people were quite happy with it. But every here and then, you get hiccups from the subtle probabilistic nature. So you really construct these stochastic integrals as random variables. So the moment you face some uncountable, family of parameters, you're really in trouble. So that's not, it sounds like a technical issue, but there's really a problem of robustness. The other problem is if I were to give you two realizations of a Brownian path, and I ask you to tell me about the corresponding stochastic integrals, what are you doing? You have no idea. And you don't know that they're close to each other. So rough path theory fixes all that in a quite decisive way here. And I have to go back to, now time is running quickly now. I have to go back to this expected signature of Brownian motion, because what I blurred over deliberately is or was the meaning of these iterative integrals. So stochastic integration. So at some point, dt, we implicitly looked at integrals of this form here. And so, well, if you wish, you can get rid of this inner one, but just by integrating this up, and then this becomes a BS, or BT, pardon. And then you're faced to integrate BT against BT. And since everything is vector valued, you can't do it in a pathwise fashion. What's the problem here? Problem BT. So if you think of it as a sample path here, you're just short of Hölder 1/2. So any Hölder exponent less than 1/2 is fine, but and this is precisely the borderline of Young integration. So again, you need a probabilistic construction for this. Now, the simples, not going into this, but in case you're not from the probability community here, you sort of can guess it by looking at the Brownian increment, say in L2. And then remember, Brownian increments are normally distributed with variance T minus S. So therefore, L2 norm, this will be like T minus S, right? This was L2, so with some Gaussian tricks, you can beef it up to LP. So that means you can get this as an estimate in certain base of spaces, and then if you switch to a base of infinity space, you lose a little bit by these embedding theorems. This is how the 1/2 minus comes from. Or use Kolmogorov or Garcia, Rodomich-Ramsey, or whatever you know. Okay, so let's look a little bit on stochastic integration here. And I apologize to the probabilists here because they will be bored for a few minutes. So there are two things you can do. The one is you can say, well, I remember my Riemann-Stieltjes integration, and what I should do, so limits here to be confirmed and to be discussed, but what you should do is, look at some partition of my interval where you want to integrate, so everything is 0t, say. So you look at some partition, a generic interval is called ST here, and then you just freeze your integrand and hit it with some increment of your integrator, and then, fingers crossed, you hope for the best, and it actually works. So if you give the interpretation of this limit as a limit in probability and then uniformly complex, so this converges, CUB, and it converges to the Ito integral. So Ito. And if you prove it, you will need martingale stuff. And okay. There's a different point of view, which is preferred by physicists, which is to say, well, hold on a second. Brown motion is rough, but never mind. We mollify. We convolute with some, kernel. And then I have no problem, because my dB epsilon is now suddenly a b epsilon dot, if you wish, dt. And then you do your integration from 0 to t, and life is good. And then you can say again, well, if I can take the lim here, so here the limit is, if you want, so you should look at some sequence of partition with mesh to 0, and here you should take epsilon to 0. And again, it works. Right? And this is what's known as the Stratonovich integral. And I think it's fairly custom these days to make a little round here for Stratonovich. Okay. But the strategy, or the fortune, depending how you view it, is that they are different, right? So this one is not, right? I mean, if you do stochastic modeling, this is a, you need to scratch your head, because you really have to make up your mind what you want and what it means, etc. And if you take now an analyst's point of view, what the real problem is here, so the real problem here is, I mean, just formally take the Schwarz derivative in t here. What you're trying to do here right? So if f is nice, as nice as you wish, then here what you can hope for is 1/2 minus Helder. Right? I mean, unless f is trivially 0, so it can be at best have the regularity that you have from B. Now here, okay, let me not get into a detailed discussion of negative Helder spaces, but if something is alpha Helder, its derivative should be alpha minus 1 Helder. So you have here 1/2 minus 1. Well, we could have computed this. Minus 1/2 minus Helder. Right? And so if you look up, classical texts on when can you multiply elements in base of spaces, here base of infinity spaces, the exponents need to add up to something greater than 0, and they plainly don't. So this is why you can't do it in a robust way. And what you see here with Ito Stratonovich is a manifestation of the fact that you can't do it in a robust way. You can still do it, but not in a unique way. So, well, it surely doesn't mean that all this is useless, because, I mean, we know it's not. But what it means is you can't just freeze omega and everything works and you always get the same thing. It means you have to be careful. Okay, sometimes you can do a little trick, and I should mention it at least. So when we came here in the very beginning, let me go back here and do what you hate in classroom when your teacher does it. So if you carry out the first integration here, then it's just an integral from 0 to 1 or t, doesn't matter. And if you were in a scalar setting, right? So B is one-dimensional, you don't need any tensor product, then, well, if you remember calculus, and you take the derivative of 1/2 b squared, and that's pretty much it, right? So there's every good reason, if you do it up to time t, to say that this is, by definition, 1/2 bt squared. Yeah. This shouldn't be true if b is smooth, and then this here depends continuously in every possible sense on the path. So this is a natural way of defining this one for all continuous b, actually. So in a sense, if you're lucky, you can impose a chain rule and cheat the analysts. But in general, you can't. The moment you do a tensor product here, the moment you have to deal with ij here, and they're not the same, this doesn't work. Okay? So I'm just saying sometimes you're lucky, and there are many papers in stochastic analysis where people have used this luckiness, really in a central way, but then there are 50 pages around it doing other things. Well, so you can't get around Ito Stratonovich, that's all I'm saying here. You can relate these two, Ito versus Stratonovich, and in fact, let me just spell it out when you do this B Ito. Okay. So we have so I'm not indicating the integration here, but let's look at the second order iterated integral of Brown motion against itself in a vector valued setting in the Ito sense. Well, you get something, whatever it is. You can do the same in the Stratonovich sense, equals, and the only thing I change here is I put in the Stratonovich dp. Right? And then it's a little exercise in stochastic analysis that I'm not going to do, that this actually is precisely the B Ito st plus a little correction, which has the form 1/2 t minus s identity matrix in dimension d. Okay? So the reason I wanted to point this out, you remember, or maybe you don't, but we looked at this Fawcett formula, expected signature of Brown motion. And I told you there, basically, at some point you have to be honest about these things here. And we did reduce it to the second tensor level, so that's what I'm doing here. And if you do it in the Ito world, well, then you get something very boring because this is 0. But if you do it in the Stratonovich world, you just take the expected value here, Ito still disappears, and here you have that 1/2 identity matrix that we saw in Fawcett's formula. So you can see it as an Ito Stratonovich correction term if you want. Okay, now let's understand on a deterministic level what's going on here. Why is rough integration or stochastic integration so unstable? I mean, I'm just elaborating on this issue here, really. So, and I want to do this by an example that adds tremendous intuition to the whole business. And we are on our way to sort of do rough bars now. So we have a good idea about the troublemakers, these iterated integrals, right? I mean, at least they're the first sign of trouble. So can we get some deterministic view on And, well, I still want to look at these iterate integrals. So dx tensor dx. And I take x, I want to introduce a parameter n, and there's some running time t, so this is a little abusive here, but you know what I mean. And the idea is very simple. You spin around the origin, and you shrink down to nothing. So this path will converge uniformly to 0. But I do it in a way that these iterate integrals do not disappear. And this is very easy to do. 1 over n, and then, okay, so I should specify where I am. I'm in R2 here, and I will identify it with the complex plane, so I can write complex exponentials. And then here it's 2 pi I, and then n square t. Okay? So I shrink to 0, but I spin around like crazy. So two things happen. First is this converges to 0 uniformly. I mean, this is just order 1 uniformly. That's easy. So what happens at the level of iterate integrals here? Well, let me draw a little picture. There's a nice interpretation of this matrix here. Namely, if there's some path x here, it's not the one I'm looking at here, but just some path, then you can look at the signed area between the path over the interval st and the little chord that you put in here, and you call this AST for area. But it's the signed area with multiplicity counted, so that in particular, all this green formula stuff works. And so the observation is simply that AST here is the antisymmetric part of XST, which is the one I use here. Okay? With here S less than U, less than V, less than T, U, and V if you want. I mean, again, immediate application of Green's formula. Now, you see what's going on here. On the on the symmetric part, you're not worried, because there you can do some integration by parts and reduce it to the increments of the path itself. So the symmetric part will just as fine go to 0. But the antisymmetric part will not. And here's why. Well, you spin around. The radius here is 1 over n. So the area is order 1 over n squared. You do it n squared times, so the area is not going to disappear. So, but this guy here, in fact, it converges, and I cooked it up in a way that it converges, right? We just have a finite limit at the area. If I speed it up further, I can make it diverge. I can do whatever I want here. Okay, so these guys are troublemakers, these iterate integrals. And now on my slide, I wrote politics. If you can't fight your enemy, you bond with him. And that's exactly the philosophy of rough path. So instead of trying, but without any hope for success, to understand the map from x to some integral or solution of a differential equation, you take the troublemaker on board and just say, well, let's put them together, and maybe everything I want to do is a stable image of these two. And that, in fact, turns out to be true. So if you want, this is the short version of Lyons here. Lyons. And I will give a more detailed version later or tomorrow morning. So pathwise stochastic integration, and then SDEs, stochastic differential equations and all that, possible as function of B. So there are moments when slides are definitely better. This is bold. Okay. So punchline is, you take your Brownian path, you take this iterated integral, and together you can hope, and in fact it's true, that you get a robust theory. Now this is a little loose, so we should try to do a little bit more detailed here. And so I have 10 minutes left, and I think we can at least go for the definition of a rough path here. Now the theory is entirely deterministic. So at some later point, you have to show that Brownian motion plus this iterated integral satisfy with probability 1 the deterministic assumptions that I'm going to write down. There's a clean separation between analysis and probability. And in some sense, you know, analysis wins. I mean, this is where the real work comes in. Okay. So now rough paths. And don't laugh, but I will again start with a smooth path, but this time only for 20 seconds or so. Smooth path x. And again, we're on some fixed time horizon, 0t. And I will collect 3 properties that I like. And these 3 properties will be a definition, and this will be the good definition. Okay. So the 3 properties I like are the following. I can cook up a second order increment here in the way we have already seen it. So, right, dxu dxv, and if you want to be more explicit, you can do it as t, and then x su tensor dxu is the same thing. So this is just a definition here. And I want to observe 3 things. The first one is an analytic condition that tells me how bad can things be. Okay? So I call it analytic condition with some Hölder exponent alpha. And the condition is simply to say I want that my path has increments which are alpha Hölder. Now, of course, if I have a smooth path, I have alpha equals 1 here, right? But that's okay. The second remark I want to make, so you can think alpha equals 1 if you want, right? The second remark is that if my path here is alpha Hölder with exponent 1, which means it's Lipschitz, then it's a trivial exercise to see that this here is of order t minus s square. So there's a 2 alpha here. And of course, if it holds with alpha equals 1, then it trivially holds for any alpha less than 1. So that's one condition I like. Okay. The next one is something you've already seen in a much more complicated setting, namely chance relation. So here we're doing something much, 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 much simpler. And chance relation told us how you can batch these things together, these iterated integrals. So if you spell it out on level 2, which is all we're doing, then this becomes very simple. This will become something like xst plus xst tensor xtu, and then tu plus bottom plus equals. Okay. So this is precisely how you patch it together. Tu. Chance relation spelled out on tensor level 2. Really easy. And then the chain rule. And the chain rule is really, remember in the beginning I told you when you have a scalar setting here, then you can cheat the analyst and come up with a robust definition of iterated integrals. Well, this depends if you like a chain rule. So if you like chain rules, then you can impose it as follows. 2 times the symmetric part of xst equals xst tensor xst. And of course, these things need to hold for all Ts in your interval of consideration and here uniformly. So what's the meaning of this? This is just a, so if you start with a smooth path, and we still have a smooth path here, then this, it's not a definition, this is a property, right? It's something you check in two lines by using the product rule for differentials. So now here comes the thing. Now we consider a rough path. So by rough path, I just mean for a second a not smooth path. And which are the properties we like? Well, this here I have to give up, right? I can't write it down and define it this way. There's no way. But I can look for a couple x and some Manifold x such that 1, the analytic conditions should hold. Now, which alpha? Well, hopefully alpha significantly less than 1, otherwise I'm not doing something interesting. And the regime I certainly want is alpha less than 1/2 in view of Brown motion. So here we're looking at one iterate integrals. It turns out you can go down to alpha a third, which is plentiful for Brown motion. So alpha can be in this Brownian regime of Held exponent between a third and a 1/2. And you know, again, the Brown example, you can go as close as to 1/2 as you wish. But the deterministic theory just tells you need some alpha between a third and a half. And then this pair here comes with algebraic relations. This one, chain, and this one, the chain rule. So as a matter of notation, you can discard of the chain rule, in which case it's called an alpha-Helder rough path. And if you take the chain rule, then it's called a geometric alpha-Helder rough path because it's sort of, you know, as a chain rule, it preserves the if you want first order calculus, which you want in geometric. Okay. So I have 2 minutes left. I guess I can write it out. It's important enough. So definition: a pair such that x and such that okay, I'm terribly sorry. It's the most important word here. Okay, it's just what I said in words again, written on the blackboard. And if you add this chain rule, or then it's called a geometric. Okay, here it is. Now, I know you're hungry, and we should stop. I just want to make one remark. This looks a little bit obscure. I mean, this is not a path anymore. It's a pair of two objects. And one is a path, and the other one is somehow a two-parameter object. It is really a path. It's just a little bit hidden here, because if you think about it, Chen's relation tells you exactly how these generalized increments batch together. So if you know, so I'll put this up here. So nota bene. So x 0t and this guy from 0t determines the rough path. And why is that? Well, again, if you know what's going on from here to time s, and then again from here to time t, you can work out from chance relation what's going on here. Right? You just apply this with 0, and then here it's 0, and this will tell you what some further iterative integrals are. So in that sense, this is plainly a path. T maps into the sky here. In fact, in the geometric case, this takes values exactly in this space G2 that we had earlier, this free nilpotent group in the geometric case, right? So what I want to emphasize is, don't despair. This is not just some silly definition with obscure objects. These are paths. And I will make this point tomorrow again, that geometric rough paths are really genuine paths that take values in the free nilpotent group. And they are precisely alpha Hölder continuous with respect to the Kano-Karategori metric on these free nilpotent groups. Okay? So these things here, this is precisely the grading that you have in the Kano-Karategori metrics. Okay? So I'll make this more explicit tomorrow. So this is the hands-on view. You don't need to know geometry, but tomorrow I'll give you a little more. Thank you.